Hello and welcome to a new video. Yay, I'm not dead. So as many of you will know, this is my first video for quite some time, and I'd like to say I've got something special planned for you, but we're going to make a maze. That's the gist of this video, MazeGenerator. Also, since my last video, we crossed 10,000 subscribers, which is insane, and I'd like to say I've got something special planned for it. But we're making a maze. So I don't know, maybe we can do something special for 10,000 subscribers after the fact. If you've got anything you'd like to see that's not a cooking stream, let me know in the comments. So, to the maze making. The way we're going to make the maze is we're going to use what's called a recursive backtracker. So essentially we create a grid, and each grid cell has 4 walls. And then we make a little algorithm that just basically digs its way through these walls. It finds a path from one part of the maze to another, and on its way essentially knocks down walls. It's basically we're sending the Kool-Aid man running through this grid of walls. We have valid and non-valid cells. Non-valid cells are cells that we've already visited or are the edge of the map. So if the next cell is outside of the boundaries, it's non-valid. If we've already been there, it's non-valid. And then when the little algorithm encounters a dead end, so there's no neighbors that it can move to that are valid, it retraces its steps until it finds a neighbor that is valid, and then it carries on again. And it basically does this until the entire map has been covered. So it's surprisingly simple to do. Even I was able to figure it out. So that's what we're going to do today. So the first thing we need to do is go into our scripts, make a new script, and we're going to call this one MazeGenerator, and that's going to be our main script. But before we get into the MazeGenerator script, we actually want to make a different class called, we're just going to put it in the MazeGenerator.cs file, but it's a different class which we're going to call MazeCell, and this is going to hold the data for each individual maze cell. Random hashtag there. So in here we've got public bool visited, and as I said before, this is literally just going to tell us if our little algorithm's already been to this cell or not. Then public int X and Y. That is exactly what it sounds like. It's an X and Y position. And then we're going to do public bool top wall, public bool bottom wall. And that's all we're going to have for each cell. And the reason for that is because if we have all 4 walls in every cell, then we have to knock down 2 walls, if you get what I mean, because we have the top wall of one cell is the bottom wall of another cell, or left wall of one cell is the right wall of another cell. So if we have all 4 walls, we have to knock 2 walls down every time we carve a path through. So each cell is only going to have a top wall, not a bottom wall. Each cell is only going to have a top wall and a left wall. And then the bottom wall and the right wall of this will be the top wall and the left wall of the next cell. And then we have a little bit of extra code we need to add at the end for the very bottom and the very right of the map, but we'll get to there. And then just for convenience sake, we're also going to have a function to just return the X and Y position as a vector2 int. And all this does is return a new vector2 int using the X and Y value. So the last thing we need for the maze cell is a constructor. We're never going to be initializing it without any values, so we want it to take in an X and Y value. And then the first thing that we do is we put in the X and Y value. So it's this.x equals X, and this.y equals Y. And then the next bit, we're just going to say whether the algorithm is visited. I'm pretty sure this would be false by default, but let's just make sure. We don't want anything to say true until it has actually been visited. And then by default, we're going to set top wall and left wall to true. So all the walls are going to be active until we decide otherwise. So basically, before we send our little algorithm off into the maze, this is just going to be lots of cubicles with no way in or out. So that's our maze cell function. Now we can go up to the engine of our script today. There's quite a lot to do in here. First thing we want to do is create a range for this, which I'm going to say 5 minimum, because anything under that, what's the point? And yeah, I mean, how high you go is entirely up to you. I've gone as far as 500, and my computer managed to spit it out in a reasonable amount of time. But it's worth remembering that the bigger this number, the longer it's going to take the maze to generate. So I'm going to stick with 500. You can play around with that, do what you want with it. And the value that range is going to apply to is going to be an int called maze width and maze height. And we're actually going to set these to 5 by default, just because when you first add something in the inspector, it's not, even when you've got a range on it, it's not until you actually modify it. So this just ensures that we can't accidentally try and initialize it with a 0, 0 width and height, because what would be the point in that? And then after that, we need a public int start x x start y. This can be 0, 0. This is literally just what the position in the maze that the algorithm is going to start from. Every time I've messed around with it, I've just left it at 0, 0. I haven't moved it around to make sure the algorithm still works and stuff, but I basically just leave it at 0, 0, which means that it always starts in the bottom corner, left-hand corner of the maze. You could have it any of the corners, you could have it in the middle, you could have it start on one of the middle of the edges. It's entirely up to you. Next, we need an array of maze cells, and this is going to be our maze itself. This is where the bulk of the information that we need is going to be stored. Then we need a vector2 int, which is going to be called current cell. And as our algorithm makes its way around the maze, this is going to represent the cell that it is currently looking at. And we're just using it as a vector2 int to point to where in the maze we are currently looking. So let's get into the start. First thing we want to do is initialize our new maze. So maze equals new maze cell, maze width by maze height. Thank you, Visual Studio. Saving my typing today. And then we need some for loops. So for int x equals 0. And then, yep, that's right. Thank you again. And then again for the y. So that just loops through our whole maze, basically, however big we've set it. And then for each one, we're going to say maze x y equals new maze cell, and we need to pass in the x and y values so that cell knows where it is in the maze. And that's that. So the next thing we're going to do is we're going to come down here and we're going to create a public enum. And this public enum is just to make life a little bit easier. It's just directions, and all it is up, down, left, right. And you'll see why this makes life a little bit easier shortly. And when I say shortly, I mean right now. So the next thing we need is a function that, well, first off, we need a list of these directions. So the list is just going to be direction. We're just going to call it directions equals new list direction. But instead of just leaving it blank, we're going to put, okay, so Visual Studio is not always as helpful as I'd like. We're going to put the directions in there. So direction dot up. Doesn't matter what order you put these in. That's kind of the point of why we're making this list in the first place. It's so that we can randomize it. I've just been going up, down, left, right because the cheat code for Sonic the Hedgehog. Left and right. Oh, sorry, this actually needs to be inside the function that we are working on. It's not like it's a basic coding or anything. So that gives us a list of our 4 directions that we can go. We can only go up, down, left, right. There's no diagonals in this maze. And then the next thing we want is a function to spit out this list in a randomized form. So to do that, we say list direction, and we'll call it get random directions. Now, there's going to be a lot of coding in this video before we actually see anything happen, so you're going to have to bear with me. You know, trust me that I've tested all this and that it will eventually work. I mean, if you're seeing this video, it means it eventually worked, because if it didn't work, I wouldn't post it. So the first thing we do is we want to make a copy of our list, because we don't want to mess with this list because we're going to need it again. So we want to make a copy that we can chop and change and modify. So for the sake of naming, we'll just call it dir, because there's only so many times you can say direction without using the same name. List direction, and then in these brackets we want to put directions, and then that will make the new list a copy of this list. So it's just going to have up, down, left, right. And then we want to make another list, and this is going to be the list that we're going to put our random directions into. So this one is going to be an empty list, and the next step is to loop through it. So all we're going to do is while dir.count is greater than 0, loop. Because what we're going to do is we're going to loop through and pick a random one from this list here, which is a copy of this list. So we're going to pick a random index, and then we're going to take that out, put it in this list, and remove it from that list. And that way this list will contain the same 4 elements as this list, but they'll be in a random order. And then we keep going until this list is empty. So first get our random number, and that's just going to equal random.range. Yep, that's correct. We'll go with that. And then random.add. Wow, Visual Studio's really on it today. You could just let Visual Studio do this tutorial. And then finally, dir.remove at rnd. And then we're just going to loop through that. And when it gets to 0, when dir's empty, we are done. So at the end of the function, we're just returning rand dir. So we call this function and we get a random list of directions. So it could be down, up, left, right. It could be left, down, up, right, etc. You get the idea. And the next thing we're going to want is a bool for checking whether a current cell is valid. Now, as I mentioned earlier on, the conditions for valid is that the cell has not been previously visited and it is within the boundaries of the map. So it's fairly easy to check whether it's valid. They're the only things that we need to worry about. So all we're going to say is if x is less than 0, or y is less than 0, or x is greater than maze width, and it needs to be -1 because we're starting at 0, we're not starting at 1. And then same again for y, and then the last condition, or maze xy dot visited. If any of that is true, any of these conditions return true, then we're returning false. Else return true. As long as none of those are met, we can return true. If not, we return false. And then we need to move on to another function which will check. It's going to use this function that we've just created. Well, it's going to use both these functions we've just created. And this function is going to return a vector2 int, and it's going to return the vector2 int of a valid neighbor. So we're going to pass in, well, we're not going to pass in because it's using the it's using this value. It's just going to look at the current cell. It's going to look at all the neighbors of the current cell, and it's going to return the first neighbor of the current cell that is valid. So the first neighbor that is not visited and is not outside of the boundaries of the map. If it can't find one, it will just return the current cell as it was, and that's how we know that we're at a dead end. If it returns the same cell as the current cell, that means we're at a dead end and there's no valid neighbors, and then we'll get to what we do then. But for now, let's sort this part out. So to start with, we're going to want a list direction random, and we're just going to use get random directions. So that's calling this function up here. It's getting us a list of directions in a random order. And then we want to take caps lock off, vector2 int neighbor, which is going to equal current cell. If by the end of this function it still equals current cell, then we're at a dead end. So now we need a switch case, and basically we're going to check which direction we are currently facing. Case direction dot up, and if that's the case, then the neighbor vector2 int y value is going to be ++. So basically we're bumping up. Oh, sorry, that shouldn't be int. That should be that should be I. I'm actually missing a for loop out here. So up here we want to loop through all of the directions. For int I equals 0, I is less than random.count, and then that should encompass the switch and the declaration of the new vector int. So we're looking at each direction as we loop through. If at any point we get a valid cell, then we break out of this loop and we're done. So if the current direction is up, then the neighbor, we're just incrementing the y value to say up, and then we break. And we can just copy this for the rest of them and just change it. So if it's down, the y value is minus because we're looking at the cell below. If it's right, then the x value is incremented, and if it's left, the x value is decremented. Copy my little notes in here. And then at the end of it, we do a little check at the end of each loop. Is cell valid? And we just pass in the neighbor's values, and if the cell is valid, we return neighbor. That's our vector2 int that we are returning here. However, if it's not valid, we go back to the top and we try the next neighbor, or the next direction, sorry, and we do it again. And we do that until we're out of directions. And if we get to the end of the directions list and we haven't returned a valid neighbor, that means that there are no valid neighbors. We're at a dead end, and we just return current cell. So the next thing we need is a function that will set the wall flags. I think I've deleted one of my parentheses here. So this function we're going to call void break walls, going back to the Kool-Aid Man reference that I was talking about. So this is going to take in a vector2 int primary cell. Essentially, that's the current cell, the one that we're looking at, and a vector2 int secondary cell. Strictly speaking, we could just use the current cell reference, but I guess this makes it more independent. So all this will do is we pass in two cells, and this algorithm is going to work out which walls need to get broken down. And because we can only go in one direction at a time, we don't need to look like, if one direction comes back as true, then we can just ignore the rest. So we can use if-else statements for this. So if primary cell.x is greater than secondary cell.x, that means that the primary cell is to the right of the secondary cell. So which means the primary cell's left wall needs to get broken. This can be a bit of a mind melter to follow along with. So we want the primary cell's left wall. And then all we do is we just say maze primary cell.x primary cell.y left wall equals false. And this is where the top left comes in, because obviously if it was the right hand wall, which it will be in a second, we will be knocking down the secondary cell's left wall, not the primary cell's. And obviously there aren't any right or bottom walls. So then we say else if primary cell.x is less than secondary cell.x. We'll just copy this for the sake of saving my typing. In that case, we want to set the secondary cell's left wall to false. And then we'll copy all of this because it's essentially the same thing, but we're just doing the top and bottom walls now. So if primary cell y, I think this one actually wants to be less than, primary cell y is less than secondary cell.y, this would be the top wall. Yeah, so if primary cell's y is less than secondary cell's y, that means primary cell is below the secondary cell, which means primary cell's top wall needs to be removed. And then vice versa, if primary cell's y is greater than, that means primary cell is above secondary cell. So secondary cell's top wall needs to be removed. And I'm just going to scour over this a second to make sure I've definitely typed everything in correctly. Okay, I think that's right. So now we're on to the carving function. This is basically the main function in a function called MazeGenerator. This is the part that does the generating. I'm going to start off by naming it, which is going to be carve path. It's going to take in an int x and an int y, and that is the function, that is the position that it starts in. So we've got this start x and start y, which we're just going to pass directly into this when we actually call it. But if you wanted for some reason to give it a different position when you called the function, you could pass in a different start x and start y, or you could make it random. It's entirely up to you. And just for the sake of good practice, the first thing we're going to do is a little check just to make sure that whatever start position we've passed in is actually valid and within the map. So if x is less than 0 or y is less than 0, you know what, I'm just going to copy this bit because you get the idea. You don't need to see me type it. So basically we're saying if x is less than 0 or y is less than 0, or it's greater than maze width minus 1 or greater than maze height minus 1, it's outside the boundaries and we can't start from there. So I'm just going to set them to 0 and put up a little warning here just to let the user know y is being set to 0. You could do what you want here. You could have independent checks on x and y so that x, if y is greater than outside the boundaries of the map, you could still keep x where the player set it or the user set it, or you could have it randomized if it's outside the boundaries. It's entirely up to you how you handle this part. The first thing we need to do in the actual carving path part is to set the current cell to a new vector2 int xy. And then we need a list of vector2 ints, and this is going to be essentially the path that we take. And this is for the recursive backtracker part, specifically the backtracker part. We do need to backtrack in places, and we can't do that if we don't know where we've gone. So this is going to keep a list of where within the grid positions that we have been on our little path. And then when we need to go back over those positions, we can just look at this list and it'll tell us where to go next. So the next thing we're going to do is loop until we hit a dead end. So in order to do that, we're going to create a bool called dead end, and we're going to set it to false. And then we're going to go say while not dead end. So as long as dead end equals false, we keep looping. And then within that loop, the first thing to do is to get the neighbor that we're going to look at. So vector2 int next cell equals check neighbors. So if you remember, what did I call that? Did I not call it check? I called it check neighbor. So you know what? It should be check neighbors. It's checking all the neighbors, not just one neighbor. So that's going to get us a cell that is valid or not. That's the next part we need to check. So if the cell has no valid neighbors, that means next cell is equal to current cell, and we need to handle that. But we'll get to that in a second. We'll come back to that in a second because there's a lot to deal with in that little if statement. So we're just going to do the code here that we use if there are valid neighbors. So assuming we've got a valid neighbor, that's what this else means. The first thing we do is we break walls. Current cell, next cell. We just pass in those two and we let that function break the walls. Then we want to say maze current cell.x current cell.y visited equals true, because obviously we've been there now, so we want to make sure that the algorithm knows we've been there now. And then we say current cell equals next cell, because we've moved on from the current cell and we are now in the valid cell that we've just smashed a wall through to. And then finally path.add current cell, so that now becomes part of our path. Now hopefully that's fairly self-explanatory. So just to recap, assuming that we find a valid neighbor, we break the walls between the current cell and that valid neighbor. We set the current cell visited to true so that we know that the next time this cell isn't valid, so we don't just start coming back on ourselves. We set the current cell to that valid neighbor, which means we've moved into that cell now, and we add the current cell to the path so that that is now part of our path. So now we need to go deal with what happens if we don't have a valid cell. So this is if we're at a dead end. So the first thing we need to do is loop through our path, but we need to do it backwards. So it's I equals path.count minus 1. Yes, what Visual Studio said. And we're looping through backwards because obviously the last thing we added to the path was added to the end of the list. So if we started at the top of the list, then we'd be jumping right back to the beginning of our path, and we don't. We want to go backwards. For each one, we say current cell equals path I, path.remove at I, and the reason we do this is because we don't want to, like, once we've backtracked, we're shortening the path. Think of it as we're going back and removing each one from the path list, and then once we find a valid cell, we go off on that way, and it's almost like we've redirected the path. We don't want the ones that we've backtracked over to still be in the path list. And then it's next cell equals check neighbors again, and then down here we want to say if next cell does not equal current cell break. So what's happening there is if the next cell doesn't equal current cell, that means that we backtrack to a point where we found a cell that has a valid neighbor. So then we're going to carry on essentially with the loop using that valid neighbor. So the loop will go back to the top and then it's going to carry on from wherever in the path it is. This check neighbors up here, strictly speaking, it's not the most efficient way to do it because essentially we're checking neighbors twice when we could be doing it once, but I'm trying to keep everything broken out so it's easier to follow. But really you want to go directly from this bit to this bit. But just for the sake of keeping the code looking, I hope, understandable, we're going to let the loop go back round once more. This check neighbor is going to find the same neighbor that this one did, and then this time we're going to go straight to this bit because it will have a valid neighbor. However, we might not find a valid neighbor. Maybe we've completely exhausted all routes, there's no more valid neighbors left. So if that's the case, we say if next cell is equal to current cell, dead end equals true. Now we're going to be breaking out of the loop. Basically, we get up here, here, if next cell equals current cell, it means we're at a dead end, and then we attempt to backtrack and find another cell. If we backtracked all the way through the path, through our previous path, and we haven't found any valid neighbors, then that means that we've exhausted all options. Now at that point, what you could do if you wanted to be absolutely thorough is you could search through the entire maze grid and look for unvisited cells and then start the path algorithm again from that point. I've found that just leaving this part here makes a plenty good enough maze for what I want to do. But if you wanted to be super thorough, you could do another search through all the grid, find cells that aren't visited, and then start your path algorithm, your carve algorithm from those cells. So you'd pass in the X and Y of the unvisited cell that you found. So that is pretty much all of the maze generation algorithm. We're going to go back up to the top now where we've got our start function, and we're going to change the start function to a public maze cell array, and it's going to return basically the maze array that we create. So it's all going to be the same. None of this is going to change, but then just before the end of it, we will type carve path start X start Y. Again, if you wanted to start somewhere else, you could put it in there, and then we're just going to return the maze. And the reason we're doing that is because we're going to be calling this from a different function, from a different script, sorry. And that is it for the MazeGenerator script. So let's just go back into Unity and we're going to create an empty object, which I'm just going to call maze. Let's just reset its position and we'll just drop our MazeGenerator thing on here. And you can see our start X is 0, 0. That's fine for me. I mean, you can put them wherever you want. And our maze size is currently 5, 5. I'm going to bump it up to, let's say 20, just so we can see, you know, let's go 30, just so we can see something when we actually start generating the maze. So the next thing we need to do is create a new script, and this one's going to be called maze cell object, and this is a short script that's going to go on the actual objects for each cell. So we're going to create a prefab that represents each cell of the maze that's going to have its 4 walls, and then this script is going to handle which of those walls we get to see. So serialized field, because these don't need to be public, game object, and we're just going to say top wall. That's just getting as a reference to the game object, and then it's going to be the same for top wall, bottom wall, right wall, and left wall. And then we're going to have a public function called init. It's going to take in bools for each one, top, bottom, bool right, bool left, and then nice and easy, all we have to do with this is top wall dot set active, and we just straight away pass in the value, and then it's nice in Visual Studio to actually be helpful. And that's it for this one. We don't need to do anything else with that. So what we need to do now is go back into Unity, and we need to create a maze cell. So all I'm going to do is I'm going to create, well, first off we need to create an empty. I'm just going to call it maze cell. Again, let's just reset that position so that it's in at 0, 0. And then in there, just to make things a bit easier to see what's going on, let's create a plane, 0.1, 0.1, 0.1. So that is a 1F plane. If I were to drop I'm going to drop a cube on because we need a cube for what we're doing next. If I drop a cube on, you can say it's 1 by 1 by 1, because a plane, when you spawn it in by default, is 10 by 10. And I've just made it 0.1 scale. Actually, it doesn't need to be 0.1 on the y-axis. So the plane is just a floor. It's completely for aesthetic reasons on this one. It's not important for the actual maze generation. You could have one big floor, you could have no floor. This is just to make things a bit more visually appealing. Now these are going to be the walls. So we'll do top wall first. And all I'm going to do for the top wall is, well, first off, let's just move it up so it's on the floor. And we're going to set, I think it wants to be this one, this to 0.05. So basically we've just squashed it to make it into a wall. And then if we put that at 0.5, it puts it on the edge of the square. And then we're just going to copy that 2 more times. This one is the bottom wall. Now I know what you might be thinking, thinking if you've been paying attention, which is we haven't got a bottom and right wall in our script. So why would we be putting a physical bottom and right wall? You'll see that in a second. It is important. This one wants to be minus 0.5, and then these two are going to be the left and right walls. So for this one, we just need to change the scale so that it's on the point X axis, that is 0.5. Oh, that's the position, sorry. 0.05, there we go. And then X wants to be minus 0.5, and all the rest wants to be 0. So that gives us our left wall, even though I've labeled it right wall. And then, you know, let's just copy that one, it'll be easier. Duplicate that one. And this one is right wall, and then obviously it wants to be 0.5. And then if we go back to our maze cell, we drag our maze cell object, and we just want to drag all of these into the correct one, because if we don't drag into the correct one, we get all manner of things going wrong when we actually generate the maze. Okay, so as you can see, we've just got a box with a floor in it, and we're going to create a grid full of these, and then the algorithm is going to activate or deactivate the walls as necessary. It's going to break through those walls. So let's just go in our prefab folder, drag the maze cell in, and then we can delete that out there. We don't need it just yet. So the last bit of coding, I promise, we need to create one more script. It's not a big one, this one, don't worry. And we're going to call this one, let's say maze renderer. So we need two variables to start with. We need the MazeGenerator class, and that's just going to be a reference to the MazeGenerator that we put in the game, that we have already put in the game. I'm going to put them on the same object, but you wouldn't need to. You just need to drag in a reference for that. And then same again, but this time for a game object, and this is just going to be the maze cell prefab, the one that we've just created. And then we want a public float cell size, and this is going to equal 1f. So what this is the physical size of each maze cell. Right now I've made them exactly one by one unity units. If you this is so you can make them any size you want, but this needs to correspond to the cell, because if not, you're either going to have the cells overlapping each other, or you're going to have gaps that you can see between them. So we'll get into a start function. This is going to run straight off the bat. Maze cell. We don't need a reference to this outside of this function, so we're just going to call it, we're going to declare it in here, and that's going to call MazeGenerator.getMaze, and that will run all of this, generate a maze, and hand back the array with the maze information in it. The reason I'm not running this in like the start or awake function and then just calling it when we're ready is because there's always a chance that that won't be done before this tries to call it. So this way it doesn't even try until this asks for it, and then this will wait until it's done. And then the next thing we're going to do is loop through, like we did in the other ones, we're going to loop through all of the maze positions. This is maze.length. This wants to be MazeGenerator.mazeWidth, and then we're going to do the same thing again there. So in here, we're going to instantiate a new cell, instantiate maze cell prefab, and then the position is going to be float x multiplied by cell size. And then y, we're just going to leave it 0 because we're only dealing with a two-dimensional map here. And then z again, float, well, it's y, but it is the z position. And then rotation, we'll just set to quaternion.identity because we don't want it rotating. And then just for the sake of neatness, we're going to pass in a parent, which will be the MazeGenerator object, just to keep everything in that hierarchy. And then the next thing we need is a reference to the maze cell object. So we get new cell that we've just created, get component, maze cell object. So next thing is to determine which cells are active. So we're just going to create bools for top, left, bottom, right, and we're going to pass them directly into our maze cell init function. So top and left is easy because we already have that in the maze cell value itself. So we can set it directly to top wall, and then same again for left wall. A little bit different for bottom and right. So bottom and right, we know for most of the cells is going to be 0. So let's just set it to false by default. Bottom equals false, and then we want to change it if we are either at the very bottom edge of the map or we're on the very right hand side of the map. So if x is equal to MazeGenerator.mazeWidth -1, right equals true. If y is equal to 0, because 0 is the bottom of the map, bottom equals true. And then finally, we just want to call MazeCell.init, and we just pass in top, bottom, left, right. And I'm just going to quickly just check to make sure I definitely put it in that order. Top, bottom, right, left. See, that could have been a big problem. So just make sure that this is the right order, that you've done this, because if not, you're going to get all kinds of weird results. Top, bottom, right, left for some reason. Top, bottom, right, left. Okay, right. left. So if we go back to Unity now, go to our maze object, drag our maze renderer on there. We want a reference to our MazeGenerator script. Again, you could have got this from get component, but whatever works. Drag in our maze cell, and now there's a lot of coding. If this doesn't work, that's a lot of coding to sit through. We press play. Okay, so something isn't quite right. We may have got our tops and our bottoms mixed up somewhere. Yes, we have indeed gotten our tops and our bottoms mixed up. So let's just rename these. Very easy to get confused when you're me. So let's reassign these and back out of here and try that again. There we go, much better. So yes, it's very important to try and make sure you get everything labeled correctly. So as you can see, we have a maze. And now the good bit about this is that those cell prefabs can be made of anything, as long as you have walls that can be activated and deactivated. You know, you can do what you want with them. Now, what I'm going to do now is I'm going to turn the recording off and I'm going to faff around with some assets, and all I'm going to do is basically, if I just get this up, all I'm going to do is change this. I'm just going to use some proper assets. Oh, no, I'll drag in a first person controller as well so we can see the maze in person properly. But I'm just going to change these assets here for something, well, these shapes for something a bit more visually appealing. So I will see you shortly. So there we have it. That is how to make a maze in Unity. A very simple maze. There's more complicated algorithms, and I encourage anyone who's interested in maze making to look them up. Maybe we'll cover them in a future video if anyone's interested in it. But yeah, that's it's fairly simple. I hope my code was clear enough. And with just slapping in some other assets and a few filters and stuff on the camera, it can look like this, which appears to be all the rage on the internet and YouTube these days. So if you don't know what you're looking at, Google Backrooms and enjoy falling down that rabbit hole. And all that's left to do now is to thank all my amazing Patreons who, for some reason that I can't explain, have stuck with me all this time through no videos. So I will endeavour to make it up to you all. But special thanks go to the Sugar Daddy / Mama Patrons, who are Dave Maldine, Reg Reed, Gabriel White, Aaron Clark, Mr. Drunken Dragon, Julian, Andrew Hansen, and Aji. And you guys will hopefully be getting a Patreon exclusive video quite soon on the card game. So thanks for waiting. Hope it was worth it, and I will see you soon. Bye bye.